Hello everyone, my name is Koji Yamamoto of CYBERNET Systems from Japan. I am very happy to be able to talk to you today. I'd like to talk about the material constitutive law for the plastic hardening of unidirectional reinforced CFRTP. By observing the material behavior of CFRTP in detail, we found that this material has a complex hardening characteristic. As you know, there are many situations in which elastoplastic properties are actively utilized, such as in place molding and so on. We are trying to provide solutions to resolve such problems analytically. This is what I will be presenting today. My talk today will have 6 parts. I will start with background and motivation of this work, reviewing some of the previous research regarding to the material constitutive law of elastoplastic problems. Then, based on that, I will explain the purpose and the specific procedure of our study. The third and subsequent topics will show the results of this study. Our study starts with a detailed observation of the elastoplastic properties of CFRTP. To achieve this, we adopted an approach that analysis technique, in other words, virtual material testing. After that, we then propose a new constitutive law for CFRTP that can represent the elastoplastic material behavior more accurately than previously proposed method. This material model will be validated by curve fitting the properties obtained from the testing. Finally, I will make a brief summary and talk about the future plan. As you know, there has been a long history of the research on the mathematical representation of elastoplastic material behavior. Here, I summarize the results that have been proposed for the yield function and hardening law that constitutes the elastoplastic material law. The yield functions mainly used to determine yield surface. Although there are many anisotropic yield functions, metal-derived models are generally used as shown here. However, for materials reinforced with continuous fiber, such as textile and UD composite, these material models does not have sufficient representational capability. So, yield functions specific to each composite materials have been proposed. Bimodal plasticity theory has been proposed for the UD composite, that is concept of our study. On the other hand, hardening rules have also been proposed in the wide variety of models. This figure shows a schematic of the yield surface before and after hardening, drawn on the pipeline. The 3 in the upper row move or expand while maintaining the similarity of the initial shape. The 2 hardening rule in the bottom row collapse the shape of the yield surface. In this case, initial surface is restricted to be isotropic. It cannot be applied to the problem of anisotropic yield surface. Above all, there are not many examples where the hardening behavior of UD composite have been accurately observed. So, there are 2 purposes in this study. First one is to observe the anisotropic elastoplastic material behavior of UD composite in detail, paying particular attention to the hardening behavior. Furthermore, we propose a new material model taking into account complex hardening behavior. I am showing a brief flow of this research. The anisotropic material behavior of CFRTP is observed by virtual material testing. In order to perform this analysis, the material properties of the resin and fiber are required individually. Fiber's properties are taken from previous studies. For the resin, the material properties were prepared by realistic cyclic test. Using the Uniaxial model created in such a way, virtual material tests with various stress conditions were carried out. From the obtained stress-strain curve, the shape and movement of the yield surface will be observed. From the obtained stress-strain curve, the shape and movement of the yield surface will be observed. We then propose a constitutive law to resolve this problem. Finally, stress-strain curve from virtual test will be curve-fitted by proposed material model. The validity of the material model will be verified from the accuracy of the curve-fitting results. Here is a stress-strain curve for pure resin. In this study, a thermoplastic epoxy resin was used as a matrix. The graph at the left-hand side is the results of cyclic loading test. We focused on the yield stress on the tensile and compressive side. It was determined here that the hardening behavior is almost isotropic. So only the properties of the tensile side were used to identify the material properties of the resin. The result is shown in the graph on the right. In the cyclic test, we were not able to test to the large strain range due to buckling in the compression side. Therefore, a separate tensile-only test was conducted exclusively for the identification of the material constants. For the isotropic elastoplastic material model, we used the Boche's law as shown here. It was confirmed that it can be fitted very well. Next, I will explain the conditions of the virtual material test conducted on CFRTP. The unit cell model is shown here. The analysis is performed based on the homogenization method. The fibers are oriented in Y1 direction. In this case, we assumed a plane stress state. Then there are three components of stress, but the normal stress for fiber-oriented component will contribute later to yielding. So we applied only two stress components, which are in plane shear stress and transverse stress. A conceptual diagram of this stress state is shown in the blue hashed area. In order to draw the yield surface, analysis was performed by varying the stress ratio of these two components. In order to observe the yield surface after hardening, the same tests were conducted for the pre-stressed condition. The pre-stressed was tested for two cases, one with pair shearing and the other with uniaxial stress as shown in the green hashed area. This is the actual shape of the observed yield surface. In the graph, the shear stress is on the vertical axis and the transverse stress is on the horizontal axis. The initial yield surface is shown in the blue and the subsequent yield surface is shown in green. First, shown on the left is the subsequent yield surface when pre-stress is applied in the transverse direction. As you can see, the similarity relationship clearly breaks down between initial and subsequent states. The green one is characterized by a large overhang in the pre-stress direction. On the other hand, in the case of pre-stressing by shear component, although there is no serious distortion compared to the results from transverse stress, it does not show the same characteristics of free isotropic hardening behavior as a resin. From the above, it was confirmed that even if the resin has isotropic hardening behavior, the UD composite has anisotropic hardening. Moreover, this behavior is dependent on the stress state. In the next slide, I will introduce the overview of the material model proposed by our study. This slide shows the yield function, hardening law, and flow rule respectively. The yield function is based on the bimodal plasticity theory. The important feature of this formulation is that it is made up of three functions which are divided into cases according to the stress state. The conceptual diagram is shown here. When shear stress is dominant, the yield function shown in green is used. If vertical stress is dominant, other yield functions are used. They are circular arcs symmetrical on the tensile and compressive sides. The hardening rule incorporates the effects of both the isotropic mode and the kinematic mode, which is expressed by the back stress. The isotropic hardening behavior is based on the Boche's law, which is same as for resin. The development of back stress is divided into the amount linked to the isotropic hardening and equivalent plastic strain component. I will explain the hardening rule in more detail. This equation is a rewrite of the hardening rule in the previous slide with three separate components. As shown earlier, in the initial state, the center coordinates of each arc is offset. This corresponds to the first item of the back stress in the three yield functions. When the material is yielded, other component will be developed. Let's first look at the isotropic component. In isotropic hardening, the yield surface maintains a similar relationship to the initial state, so it changes as shown in the red line of this figure. The important thing here is that in order to maintain the similarity relation, the center position of the arc must have moved. This is the second term of the development rule. Finally, there is a back stress that develops in conjunction with plastic strain. I will not explain in detail due to time consuming, but our model can express the distortion by developing back stress for tensile and compressive side independently. Now, I will show the results of curve fitting the virtual test results using this material model. First, I show the case where shear pre-stress is applied. The left side shows the yield surface. In addition to the results of virtual test and response of the proposed model, the results of the classical Hills model are also given for the reference. The color of blue, orange, and green lines represent as results of virtual test, Hills model, and our proposed model respectively. And the circular plot shows the initial state, and the square plot shows the post-yield state. Obviously, the fitting accuracy of the Hills model is poor. On the other hand, our proposed model is showing better fitting results than Hills model, both initially and after hardening state. The right graph shows the stress-strain curve and the load history of load step 3 shown in the left figure, where the Hills model clearly shows excessively high yield stress. The hardening behavior under transverse pre-stress was also verified in the same way. In this case, the yield surface is distorted more than the hardening due to shear pre-stress. Therefore, Hills model clearly fails to capture the characteristics of material behavior observed by virtual test. Whereas, the proposed model successfully expressed the feature of large overhang in the pre-stress direction. Not only that, the yield behavior on the compression side is also accurately fitted. The stress-strain curve for the typical stress history is shown on the right. Our proposed model captures the yield point of the virtual test well, and also we can confirm that the fitting accuracy of the stress-strain curve after re-yield region. I would like to summarize the main finding of this study and talk about a future plan. We investigate elastoplastic material behavior of UD composite. The material behavior of the resin was observed by real testing. Then, the material behavior of UD was observed by virtual material testing. As a result, it was confirmed that although the resin has isotropic hardening character, the yield surface of the UD composite tends to be distorted by hardening, depending on the stress state. In order to represent this material behavior, we proposed a new material model that combines the bimodal plasticity theory and the original hardening rule. The validity of this constitutive law is confirmed by the fact that it can accurately fit the response of virtual test. Our plan for the future is to implement a more robust verification process. Specifically, we will perform realistic cyclic test of UD composite, where biaxial stress state can be created by changing the orientation of the fibers. By comparing the experimental results with the analysis results, we hope to be able to confirm the validity of our model in more detail. This is all for my presentation. Thank you so much for your kind attention.